All right, so Vsauce has a really good video on like spinning and rotation. It's 17 minutes long, so I'm not going to play the whole thing, but just skip through different parts. So he starts talking about gyroscopes, right? I showed one yesterday. It was spinning that bike wheel. What's going on with that? So he starts looking at this rotational motion. He says, makes this point that that force you feel when things are rotating is really a centripetal force. There's some force that's pulling you inward. Okay. Okay, so not versus centrifugal. There's nothing that's pushing you outward, even though if you close your eyes, you think that's what's going on. Okay. Right. So he's looking at the satellite in orbit, and thinking, "Oh, hold on, did I miss? That's what I'm looking for here." Okay, here it is. Here it is. All right. So let's say you get a ball of just motion, just like linear motion. It's gone, and you hit it from the side. Okay. It's not going to immediately change its direction. It's going to it's got to go off on some angle. Okay. So it's still moving forward. It still has forward momentum. Right? And then you kick it to the side 90 degrees, and those two are going to add like tip to tail, right? And then it's going to follow that resultant. Okay. So now if you go to something that's rotating, so he's looking at like a single point mass orbiting the Earth, for example, right? And it similarly already has like some linear momentum at that instant. And say you like knock it from above, it's actually going to turn like that, right? Well, if you just turn that into an entire disk, then it's the same principle. It's just like you have a billion individual point masses just connected, but it's the same thing. Right? So if you have this rotating, and then suppose it starts to fall over, starts to lean over, that's sort of equivalent to like putting a force on that one side, but it doesn't actually lean towards the direction of force. It leans 90 degrees ahead of its rotation. Right? And if it's constantly doing that, that's why it doesn't fall over. Because whichever way it looks like it would want to fall if it wasn't spinning, it would want to turn 90 degrees ahead of that. But then it starts to do that and wants to turn 90 degrees ahead again. Right. So it stays up. That's why tops stay up. That's why gyroscopes stay up. That's why that even ties into this bike wheel. So he does this thing with the bike wheel. We did something really similar. Oh, yeah. I pause here. Resume. All right. So yeah, so we got this wheel, angular momentum. Yeah, I did it. You know, I have two, so right, but hopefully you guys got to get your hands on this yesterday, but if you didn't, then anyway, I guess that's been all right. So what I got lined up next here. Tom Scott, I really like this guy's channel. If you've never come across this, so he's in this rotating room, right? He's in this rotating frame of reference. Now, since they're covered, since they have these walls around them, right, they can't see the outside world. So if they stay stationary, then it would feel like they would be pushed out, although there's really a normal force pulling them in, right? Right. But the physics get really wacky. So at some point they start throwing a tennis ball around. Notice they're staying really still, because if they move too much, then the fluid in your ears that helps you keep balance goes all wacky and messes with your head. But so they're throwing this tennis ball around. It's not going straight. This really weird rotating frame of reference. Right? Anyway, got a couple other demos that probably save for tomorrow. So let me skip back here.